Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. We are today going to look at Karnaugh Maps, which is sort of like a 2D truth table in which we can use them to directly get a simplified expression from the map itself. I find them to be very valuable and very exciting to use, and I hope you find them as exciting and valuable as we go through this lesson. So let's get started. Karnaugh Maps, or K-Maps. And again, they're kind of like a two-dimensional truth table. And they have some rules in which we'll look into as we go along here, as you might expect. But let's just go ahead and draw one. Okay, so they look like a table, and they're going to be a number of cells that are going to be powers of 2, just like their rows in the truth table. And each of these cells is going to correspond to a min term from the truth table. And I'm just going to label them A, B, C, and D here. So what if we had inputs X and Y, and on the outside here we have these headers that tell us about what X and Y look like in each of these cells. So if it has a 0, that means that it's complemented, meaning it's barred, for instance, like X bar. And if it has a 1, that means it's not complemented, and so like X, okay? So that's how we interpret these zeros and ones that are at the top. So now if I were to write what A is equal to here, well, A has X as 0 and Y as 0. We sort of just like cross-reference here with the top and the side. So A is 0 and 0 for X and Y. So that means it's complemented. So A is the min term X bar, Y bar, or X not, Y not. If I look at B, B corresponds to X row 0 and corresponds to Y row 1, and so we get X bar Y. Y is not complemented because it's in the 1 column. C is going to be X, Y bar, and D is going to be X, Y. So each of these is a min term from our 2 inputs X and Y. So each cell is a min term. Okay, so that's how we get started in understanding what that looks like. So this is 2 variables, and that's where we're starting right here. And we'll go to more variables as we move along. But so this has 2 variables at the moment. Right, so I'm going to pull down. I have that's not going to work. I have a couple of drawings here, so let's see if we can pull this down and use it. Make it look nice. Okay, great. So for this next Karnaugh map, we'll call this F1. We have X and Y, and you can see 0, 1, 0, 1 already labeled there for us. And so I'm going to fill in this with actual values this time. And so not only do we have a min term there, but the min term is still there, implicitly there, but that min term now evaluates to a value of 1 or a 0. So we know if it's present or not because that's the output that we expect in the truth table. So these are the output row, the output column of the truth table. Whatever would be written in that output column, we would also put in here for those min-term rows. Okay, and we'll look in the next video at how we populate these Karnaugh maps from a truth table. So if that didn't quite make sense, that's okay. We're focusing on what we're actually doing to generate this expression. All right, so let's write an expression for F1. So this, we're going to write a term for all the ones that we see here, right? So we want a min-term for each one, if you will. And so I look at this and I see x is 0, y 1. So just like above, this would be x bar and y. Now we'd OR it with this one, which is x and y. So x, y, so like that. So this would be a valid min-term expression for this K-map. And we could have left it here, but the cool thing about a K-map is that we can use its geometry to immediately simplify our expression. And then I'll show you what I mean by changing our color here and doing what we call boxing. Okay, so I'm gonna box adjacent ones like this. And I know it's more like a circling here, but we call it boxing. And so we're gonna box this. We're gonna box cells of ones in powers of 2. So I can box 1 cell, 2 cells, 4 cells, 8 cells, 16 cells, so on and so forth. And one of our rules is that we want to box as large as possible. And we'll see that play out here because instead of having 1 box for each one, I have a box that goes around 2 adjacent cells. Another rule that we have here is that there are no zeros allowed inside the boxes. So there have to be only ones inside the box. All right. So why do I know we have to box? Well, if I look at this, I can see that I could distribute out the y and then do complementation here and end up that this is just y. So the answer here should be just y. But if we just wrote those 2 ones by themselves, we'd get these 2 min-terms. But look at what happens if I box these 2. Okay? And when we look at boxes, we want to keep what is the same. And this is an important rule. Keep what is the same. So I'm going to look at these 2 ones, and I'm going to ask about each of the variable inputs, x and y. And I'm going to ask, did they stay the same, and how did they stay the same? So for these 2 ones, I can see that x did not stay the same. It went between 0 and 1 right here, okay? But y did stay the same, and it stays the same as a 1. And so that means I can write this directly as that the output here, f, is equal to y. Not y bar, but y. And that's how we use the truth table. Sorry, that's how we use the Karnaugh map. You do it directly like that. All right, let's do another example. Let's see if I can just cheat a little bit here. Ooh, that's nice. Okay, and then we'll just scroll that up. Great. Okay, so let's call this one F2. And again, we'll have x and y. And now it looks like this. Okay, so let's go ahead and make our boxes. So we want to box ones, and we want to box in powers of 2. And so if I look at this, I could box these together, but I can't box 4, because if I tried to box 4, it would include a 0, and we can't include any zeros. So let's go ahead and start our boxing by boxing these top 2 right here. So what's left? Well, I guess there's this left, right? So I have to box this 1. And so let's go ahead and write out this expression. F2 is, well, here's a 0. So x stays the same in both of these, right? So x stays the same as 0, but y changes. So this would be x bar, because x stays the same and the 0 means a bar. And then I'm going to OR that with this one here, right? So this is x as a 1 and y as a 0. So this is x, y bar. Wait a second. I remember this. This is a consensus theorem here. And so x bar or x, y bar, this x bar and x interact with each other and actually turn into x bar or y bar. So there's a simplification that can still happen here. Why did my Karnaugh map not catch that for me? And the reason why is because we can be redundant with our ones. We want to box the biggest box that we can, even if it means including ones that have already been boxed. And so instead of having that one cell being boxed, I'm actually going to box both of these cells. And let's go ahead and put that one back in there. Don't want to forget about that. So that red box now is telling us that we're boxing both of those cells. And what does that look like? Well, that is y bar. So that y bar here comes from the red, and then the blue one is that x bar. So if we box as large as possible in being redundant in that boxing, we should be able to get down to the most simplified version of our expression from the tools that we have at this point. And so let's make another rule here. Boxing can be redundant. Okay. Great. Let's move up here and grab another item. This is my size 3 variable K-map. Okay, so if we have 3 variables, we have to make a K-map that looks something like this. So this is for 3, oops. This is for 3 variables. And so now I'm going to do x over here and y and z on this side. Now, one thing that I want you to notice right away is that we have 2 numbers on the top now. We have a 0 and 1 for x, and now we have 0, 0 for y and z, 0, 1 for y and z, 1, 1 for y and z, and 1, 0 for y and z. The other thing that you might notice is that if we look at this binary count, it goes 1, 0, 1, 3, 2. So it doesn't count up 0, 1, 2, 3. And the reason for this is that we want only one variable to change as we go from adjacent cell to adjacent cell. So 0, 0 goes to 0, 1. The first 0 for y stays the same, but z went from 0 to 1. If I were to go from 0, 1 to 1, 0, both y and z would be changing. And I don't want that to happen. I want only one to change. So we go to 1, 1, then to 1, 0, and that allows for us not to have both changing. And so we want only one variable to change in adjacent cells. Okay. So let's make some values in here. So these are the output values. This is the f, and we'll call this f3. And so this is what we want the function to do. Now these are like the last row in the truth table, like I said from before. So what would be the Boolean expression for this K-map? Let's look at some boxings. So here on the left side, I can see I can box a group of 4. And then here on the right side, it looks like there's a group of 2. And so I've gotten all the ones, and I've boxed them as large as I can. And so I'll write this expression, f3. What stays the same within these 4 cells? Well, x goes from 0 to 1. Y is 0 and then 0 again. And z goes from 0 to 1. So the only thing that stayed the same was y stayed the same, and it stayed the same at 0. And so this is going to be y bar. Or what stayed the same here? Well, it's in the same column, so that 1, 0 would be the same for both of these. So y is a 1, z is a 0. So this is going to be y z bar. Now, x did change as we went between those two rows. Okay, wait a second, this is consensus again. And so I should be able to drop out that y. So that should be y or z bar. Sorry, my bar or z bar. So what happened? Well, just like we saw last time, there's a bigger box that we can make for these two ones. And the bigger box comes from the fact that 1 and 0 is only one different from 0, 0. So I could actually wrap around and box it like that. So that's a box of size 4 that has wrapped around the K-map. So you can think of this as not just a straight line, but actually a ring, a circle that it goes around, it wraps around. And so if I have a 1 here and a 1 on the other side, they can be boxed together. And so this is the largest one we can make. This is a size 4 box. And so I look at what stays the same here, and what we find is that stays the same as z bar. And so that's why that z bar comes into play. Okay, so we have this idea of wrapping. So you can wrap around K-maps. Okay. All right, let's move on to a 4 variable situation. And I want to grab my 4 variable table. I think these make it look nice. Okay, great. So this is 4 variables. So we're going to have w, x, y, and z. Okay. Right away, I want you to notice that in the rows now, we go from 0 to 1 to 3 and then to 2. So the same reasoning applies. We don't want to change more than one variable as we move through the rows. I also want to remind you that we can wrap. I keep on thinking of like freestyle rapping. Hey, off the top of the dome, we'll do the K-map. All right, whatever. So, edit, delete. No, I'm just kidding. So that's an important point to understand, is that they wrap in both of those directions there. So let's build one of these out. And so I want 1, 1, 1, 1, 1, 1, and 1. So if this were a truth table, it would have 16 rows, because 2 to the 4 is 16. Every time we add a different or another input, it doubles the number of potential combinations that we have, right? So we have 16 rows here in the truth table, which corresponds to 16 cells in our K-map, each of them representing a min term for our function. And so we'll call this F4. All right, so let's go ahead and make some circles. One that I see right off the bat here is this vertical group of 4. Okay, and then I have this group of 2 right here. And then I have these 2 and these 2, but they are across from each other. So this is going to be a group of 4 in a square. All right, so there's 3 boxes. 3 boxes means there's going to be 3 terms. And the number of literals in the term is inversely proportional to the size of the box. So if I have only one cell, that's going to have all 4 literals. It's going to be a min term. If I have 2 cells, it's going to be 3 literals. If I have 4 cells, it's going to be 2 literals. If I had 8 cells, it would be 1 literal. And if I had all 16 cells in a box, it would be just a constant, a 1 or a 0. And in this case, I guess it would be a 1 since we're circling ones. So let's go ahead and look at F4 here. I'll take the vertical one first. So what stays the same? Well, this column stays the same, and that's 0, 1 for y, z. So we got y bar z. And then let's take the 4 where we wrap around. So the wraparound uses rows 0 and row 4 or row 3 here. Okay, so the top and the bottom row, if you will. I guess that's row 2. And so what stays the same there? Well, it's W0, X0, W1, X0. So X stays the same in these 2 rows. And so we have X bar, it stays at 0. And then in these 2 columns, we have 0, 0, 0, 1, so y stays at 0. So this is an X bar, Y bar. So this is a smaller box. It's a box of 2, so I expect there to be 3 literals in my term. So let's go ahead and look at what stays the same. Well, it's all in this row, so that means 0, 1 is the same for WX. So we get W bar X. And then it's in these 2 columns. So what's the same in these 2 columns? It's the 1 for Z, so it's Z. And that is my expression. Now, think about how awesome this is. This is truly just amazing for saving us time and effort, okay? One thing is, if I count up the number of minterms, there's 1, 2, 3, 4, 5, 6, 7 minterms. So if I were to solve this with Boolean algebra, I would start with 7 terms, each with 4 literals in it, and I would have to start doing algebraic moves until I got to a simplification, right? Instead, with this boxing technique, I can visually box and then write out the simplified expression in one fell swoop, okay? And it's procedural, meaning that I know step by step what I'm supposed to do to get to the end. Instead of with algebraic manipulation, we're kind of guessing, like, well, what should I do next? How do I get to this answer? How do I get to the most simplified expression? So that's one of the best values that we have here. Okay. So I want to do one last thing, and I'm just going to erase here so I can show you this. There is a double wrapping situation of the top of the dome. And that happens when you have the 4 corners. So the 4 corners here is a situation where we're going to wrap not only vertically but horizontally, like that. Okay. So this special situation is using rows 1 and 4. So 0, 0, 1, 0, that means this is X bar. And it's using columns 1 and 4, 0, 0, 1, 0, so this is Z bar. So those 4 corners gives you the expression X bar, Z bar. And I don't know if I went to my picture there, so I'm just going to write it over here as well, just in case. That was a little bit longer. I appreciate your attention. I hope you got a lot out of that. K-maps are very valuable. They're very useful. I've always enjoyed them. I hope you enjoy them as much as I do. That's it for today. I'm Mike Stanczyk. This is Digital Electronics Classroom. Have a wonderful day.